Good morning, everyone. I'm excited to welcome you to today's presentation on wastewater treatment ponds. Today, we'll explore how shallow ponds, typically 3 to 5 feet deep, are used to treat wastewater naturally. We'll look at the processes involved, like how solids settle and decompose, evaporation, and how algae help consume nutrients. So, let's get started and discover how these ponds play a vital role in wastewater management. Now, let's explore how ponds treat wastewater naturally. One of the key components here is the role of green algae, which are microscopic plants floating freely in the water. These algae use dissolved nutrients like nitrogen and phosphorus. These are the nutrients that often cause problems in water pollution. They consume carbon dioxide and bicarbonate to build their body protoplasm, and as a byproduct, they release oxygen into the water. This process is quite similar to what land plants do during photosynthesis. This natural process creates a kind of symbiotic relationship between bacteria and algae. The bacteria help break down waste, while the algae utilize the nutrients and produce oxygen. Together, they form an effective treatment system that doesn't require a lot of mechanical work or intervention. This natural synergy is what makes ponds an efficient, low-maintenance way to clean wastewater before it's released back into the environment, aligning perfectly with our overall goal of sustainable water treatment solutions. Let's take a look at the historical development of wastewater treatment. Starting with ancient systems, the first wastewater collection methods in both the Orient and Europe simply discharged waste into nearby water bodies. It was a straightforward approach, but it laid the groundwork for future improvements. Moving forward to early U.S. efforts, the first ponds were built specifically to prevent wastewater from flowing into areas where it might cause problems or be objectionable. These early ponds were an important step in managing waste more effectively. As our understanding grew, the treatment process itself became recognized and better understood through performance studies. This was a key milestone because it allowed us to refine and improve treatment methods. Today, we see modern applications where complete treatment processes are implemented, offering clear advantages, especially for smaller installations where land is available. These developments highlight how wastewater treatment has evolved from simple disposal to sophisticated, environmentally conscious processes that serve our communities better. Let's talk about some of the key advantages of pond systems. First, from an economic standpoint, they require no expensive equipment, which helps keep costs down. They're also economical to construct and tend to have low energy consumption, making them a cost-effective choice overall. When it comes to operational simplicity, pond systems don't need highly trained personnel to run smoothly, and they are known for being quite trouble-free, with minimal issues related to sludge handling. Moving on to performance and flexibility, pond systems often perform as well as or even better than traditional treatment methods. They are adaptable to changing loads, which means they can handle fluctuations without a problem. Plus, they have the potential for increased design life, providing a longer-lasting solution. Finally, let's consider the environmental value. These systems can serve as wildlife habitats, supporting local ecosystems. They are also adaptable to land application, allowing for environmentally friendly disposal options. Overall, pond systems offer a practical, cost-effective, and environmentally beneficial solution for wastewater treatment. Now, let's look at some of the limitations to consider with this treatment method. First, odor potential is something to keep in mind. It may emit odors under certain conditions, especially during the spring warm-up or if the system becomes overloaded. So, managing odors is an important aspect of operation. Next, land requirements are quite significant. These systems need a large area of land, which makes them less suitable for urban environments or areas where land costs are high. It's something to consider when planning for implementation. Then, there's the issue of climate dependency. The efficiency of treatment can vary quite a bit depending on the climate. Temperature and sunlight play crucial roles, so in colder or less sunny regions, performance might drop. Finally, water quality concerns are also important. If the system isn't properly lined, there's a risk of contaminating groundwater. Additionally, the effluent might contain high levels of suspended solids, which could pose environmental challenges if not properly managed. Overall, while these systems have many benefits, understanding these limitations helps us make better decisions and optimize their use in different settings. Now, let's take a closer look at the essential pond components that play a critical role in the treatment process. First, we have flow control, which is vital for managing the movement of water through the pond system. A flow meter is used to monitor the flow rates, ensuring everything stays within optimal parameters. The bar screen helps remove coarse materials, preventing debris from clogging the system. Pond inlets are strategically placed for even distribution of water, and controlling the depth and outlet flow is crucial for maintaining proper treatment conditions. Moving on to structural elements, dikes or levees create the physical boundaries of the pond, providing containment and stability. Transfer lines connect different ponds, allowing water to flow seamlessly from one stage to the next. Recirculation lines help optimize treatment by reusing water within the system, and outlet baffles are installed to control the flow exiting the pond, ensuring proper mixing and contact time. Finally, the treatment components include the chlorination system, which disinfects the effluent, and the chlorine contact basin, where water is held long enough for effective disinfection. The effluent line then carries the treated water out of the system. All these components work together to ensure the pond functions effectively within the overall treatment process, highlighting the importance of each element in achieving clean, safe water. Now, let's take a closer look at pond operating configurations. First, we have series operation. This involves using the maximum number of cells in sequence, which is ideal for achieving the best effluent quality. I recommend this setup during summer and fall when biological activity is at its peak, as the bacteria are most active and effective during these seasons. Next, we have parallel operation. This approach is often used in winter and spring, especially in colder climates. When temperatures drop, treatment efficiency naturally decreases, so running ponds in parallel helps prevent organic overloading and reduces the risk of odor production caused by low temperatures. It's also important to note that ponds are commonly installed in series after primary treatment. This configuration provides additional clarification, helps with bod removal, and even assists with disinfection. When the detention time is sufficient, these ponds can meet fecal coliform standards, ensuring the water is safe and properly treated. Overall, choosing the right configuration depends on the season, climate, and specific treatment goals, and understanding these options helps us optimize pond performance throughout the year. Let's take a closer look at the three main types of treatment ponds. First up are aerobic ponds. These ponds are designed to keep dissolved oxygen distributed throughout the contents, which is essential for the treatment process. They are usually about 3 to 5 feet deep and don't require aeration equipment because oxygen is supplied naturally by algae during daylight hours. This natural oxygen production helps break down organic matter efficiently. Next, we have anaerobic ponds. These are much deeper, often more than 14 feet, and they operate without dissolved oxygen at any depth. Treatment in anaerobic ponds relies on fermentation of the bottom sludge, which makes them suitable for high organic loadings, typically between 200 and 1,000 pounds of BOD5 per acre per day. They're particularly useful in situations where oxygen transfer is challenging or costly. Finally, the most common type is the facultative pond. This pond combines both aerobic and anaerobic processes, which makes it very versatile. The upper portion is aerobic, supporting bacteria that thrive with oxygen, while the bottom layer is anaerobic, where bacteria can live without oxygen. These ponds are usually about 4 to 8 feet deep, with an organic loading of 15 to 50 pounds of BOD5 per acre per day. Understanding these different pond types helps us choose the right treatment method based on site conditions and treatment goals, which is central to designing effective wastewater treatment systems. Let's talk about the critical role of algae in pond health. Algae are microscopic plants that are absolutely essential for successful pond operation. They perform photosynthesis using sunlight, which means they consume carbon dioxide and, in the process, produce free oxygen for aerobic bacteria. This oxygen production is vital for breaking down waste and maintaining water quality. To give you a sense of scale, each pound of algae can produce about 1.6 pounds of oxygen on a typical summer day. Now, there's an interesting aspect to their activity related to the day-night cycle. During the day, algae actively use carbon dioxide, which helps raise the pH level of the water. But at night, they switch gears and produce carbon dioxide through respiration, which causes the pH to drop. This natural fluctuation results in daily variations in both pH and dissolved oxygen levels in the pond. It's also important to remember that algae naturally occur in ponds without any seeding, especially when the conditions are favorable. They thrive on the carbon dioxide and other nutrients present in wastewater. This natural growth plays a significant role in balancing the pond ecosystem and supporting overall pond health. In the anaerobic treatment process, organic matter in the pond is broken down by anaerobic organisms. These microbes first convert the organic material into organic acids. Then, methane fermenters step in to break down those acids further, producing gases like methane and hydrogen sulfide, along with carbon dioxide, alkalinity, and water. Now, hydrogen sulfide is often a concern because it can cause odors, but in properly designed ponds, it usually isn't a problem. That's because at high pH levels, above 8.5, hydrogen sulfide dissociates into hydrogen and hydrosulfide ions, which tend to form insoluble metallic sulfides. This means that even if hydrogen sulfide is present, the pond doesn't emit odors when the pH is maintained above that level. However, there's an exception to keep in mind. In northern climates during spring, the pH can be lower, especially when the pond is just starting up. In these conditions, hydrogen sulfide odors can become problematic and may require additional management. So, understanding these processes helps us see why maintaining proper pH levels is crucial in controlling odors and ensuring effective anaerobic treatment. When we look at factors affecting pond performance, there are three main categories to consider: physical, chemical, and biological factors. Starting with physical factors, things like soil type and surface area play a crucial role because they influence how water flows and interacts within the pond. Depth and wind action are also important, as they affect mixing and oxygen exchange. Sunlight and temperature are key because they drive biological activity and can impact the overall efficiency of treatment. Additionally, short-circuiting, which is the rapid movement of water through the pond, and inflow variations can cause uneven treatment and reduce performance. Moving on to chemical factors, the concentration of organic material is a big one. More organic matter means more demand for treatment. pH levels are critical because they affect the activity of microbes that break down waste. Solids content, including suspended solids, can hinder treatment processes if too high. And of course, the nature of the waste, whether it's organic, inorganic, or toxic, directly influences how effectively the pond can treat the water. Now, biological factors are equally vital. The type of bacteria and algae present determines how well the pond can break down waste. The activity of these organisms, their growth rates, and health all impact the treatment process. Nutrient deficiencies can limit microbial activity, reducing efficiency, while toxic concentrations of substances can inhibit or kill beneficial microbes. It's important to remember that treatment efficiencies tend to vary more than in most other treatment devices, because all these variables are interconnected. The performance of a pond depends largely on its design, which must be tailored to meet specific discharge requirements and water quality standards. So, understanding and managing these factors is key to optimizing pond performance and achieving effective treatment. Let's take a closer look at the expected treatment performance of these pond systems. First, for BOD removal, facultative ponds with a detention time of 50 to 60 days can typically achieve around 90% removal efficiency. This means they are quite effective at reducing biological oxygen demand, which is crucial for improving water quality. Next, regarding coliform reduction, properly designed systems can reduce bacteria levels by about 95%. This is important for ensuring the safety of water for reuse or discharge, as it significantly lowers the presence of harmful bacteria. In terms of reliability, these ponds can meet performance targets around 80% of the time. This indicates a solid, dependable system when properly maintained and operated. Additionally, controlled discharge ponds with longer detention times, up to 180 days, can achieve even higher removal rates. They can remove 85 to 95% of BOD and total suspended solids, and fecal coliform reductions can reach up to 99%. That's a very high level of treatment, especially for systems designed with specific conditions in mind. In some hot and arid regions, ponds are even designed to take advantage of natural processes like percolation and high evaporation rates, which means these systems can operate without discharging water at all. This approach is particularly useful in areas where water conservation and environmental protection are priorities. Overall, these systems are adaptable and effective, depending on their design and environmental context, and they play a vital role in sustainable wastewater management. When starting a new pond, the initial water fill is a crucial step. You want to add at least 1 foot of potable water or treated wastewater before introducing any wastes. This helps prevent odors that can develop if waste solids are exposed to the atmosphere early on. Next, pH management is essential during startup. Keep the pond's pH above 7.5 and monitor it closely. If needed, add soda ash to maintain that proper pH level, which is important for biological activity and overall pond health. Gradual loading of wastes is recommended during the first few weeks. Discharge wastes intermittently rather than all at once, and if possible, start during warmer months. Warmer temperatures promote better biological establishment, which is key for the pond's long-term success. Biological development takes time. You'll typically see algal blooms appear within 7 to 12 days, which is a good sign that the biological community is beginning to develop. It can take up to 60 days for a full, stable biological community to establish. A deep green color in the pond usually indicates a healthy algae population, which is beneficial for the overall ecosystem. Remember, this startup phase is one of the most critical periods in a pond's life. Proper procedures during this stage set the foundation for its long-term success, so paying close attention now will pay off later. Let's talk about daily operations, specifically focusing on scum and odor control. First, regarding scum control, it's quite common to see scum buildup, especially in spring when water warms up and biological activity picks up again. Wind usually helps dissipate this scum, but in sheltered areas, we need to intervene manually. To break up scum, you can use simple tools like garden rakes from the shore, water jets from pumps, or even outboard motors on boats. It's important to address scum promptly before it dries out and forms a crust, which makes removal more difficult. Remember, excessive scum can block sunlight from reaching the water, which reduces oxygen production by algae and can lead to odor problems down the line. Now, moving on to odor control. Most odors are caused by overloading the system or poor housekeeping practices. If you notice odors, the first step is to stop loading and divert influent to other ponds until the smell subsides. In spring, especially in colder climates, odors are common because biological activity ramps up and microorganisms consume the available dissolved oxygen. To manage odors effectively, consider recirculating water from aerobic units, using about 1 part recirculation to 6 parts influent, floating aerators, or implementing proper process control procedures. The key is planning ahead rather than waiting for an emergency. Properly managing scum and odors keeps the system running smoothly and helps maintain overall treatment effectiveness. Let's talk about vegetation and insect management in our pond. Starting with emergent weeds, it's important to keep the water level above 3 feet to discourage their growth. During the first year, pulling out new weeds by hand is effective and prevents them from establishing deep roots. If weeds become more established, raising the water level can drown them. This is known as the drown and cut method. Herbicides should be used only as a last resort, to avoid harming desirable plants and the ecosystem. Moving on to suspended vegetation, keeping the pond exposed to the wind helps prevent the buildup of light duckweed and other floating plants. Introducing ducks can be an eco-friendly way to control light duckweed naturally. Regularly skimming the surface with rakes or boards also helps keep it in check. When growth becomes excessive, mechanical harvesting can be an efficient way to remove it and maintain a healthy pond environment. For dike vegetation, mowing regularly during the growing season keeps unwanted plants under control. Planting desirable grasses on the dikes not only stabilizes the soil, but also reduces habitat for mosquitoes. Remember to use proper safety equipment when working on slopes to prevent accidents. Now, regarding insect control, the key is to keep the edges of the pond free of weeds and scum buildup. Removing scum and eliminating standing water nearby are crucial because these are prime breeding grounds for mosquitoes. Applying approved insecticides is a last resort if necessary, but the best approach is prevention, regular inspection, and immediate removal of young plants and potential breeding sites. Weeds around edges are especially problematic because they create sheltered areas that facilitate mosquito breeding and scum accumulation. Vigilance and prompt action are your best tools for keeping insect populations in check and ensuring a healthy pond environment. Let's now discuss some essential levee maintenance practices. First, erosion control is a key factor. Wave action and surface runoff can cause slope erosion, which gradually narrows the levee crown. To prevent this, we use materials like stone riprap or broken concrete rubble to protect the banks. Also, it's important to crown the levees so that rainwater drains evenly in a sheet flow, reducing erosion and water buildup. Moving on to vegetation management, planting low-growing, spreading grass on slopes that are not exposed to wave action helps stabilize the soil. Regular mowing keeps the vegetation healthy, but it's crucial to prevent grazing animals from damaging the levee. Additionally, we need to prevent long-rooted plants like willows and alfalfa, as their roots might compromise the levee structure over time. Next, animal control is vital for maintaining levee integrity. Burrowing animals such as muskrats, badgers, squirrels, and gophers can create tunnels that weaken the levee. Removing these animals promptly is essential, and any burrows should be repaired quickly to prevent potential failures. Sometimes, using riprap with a semi-porous sheet on slopes can help deter burrowing activity. Finally, seepage monitoring is critical. If you notice seepage on the outside of the levees, it's important to contact an engineer immediately. Addressing seepage early can prevent more serious issues and costly repairs down the line. Overall, these maintenance steps are crucial to ensure the levee remains effective and resilient against environmental stresses. Now, let's talk about headworks and batch operation, starting with screening and grit removal. It's important to clean the bar screens at least once or twice daily, but during storm events, more frequent visits are necessary to keep the system running smoothly. When disposing of screenings, always do so in a sanitary manner, placing them in garbage cans for landfill disposal. This helps prevent odors and fly breeding around the facility. Many installations include grit chambers to protect pumps and avoid line plugging. Grit, which contains organic matter, needs to be disposed of properly, also in a sanitary way. This step is crucial for maintaining equipment longevity and ensuring efficient operation. Moving on to controlled discharge, some ponds are designed to discharge only once in the fall or twice a year, in the fall and spring. The benefit here is that discharging during these times coincides with non-recreational seasons and when stream flows are higher, which helps minimize water quality impacts. When emptying ponds, do it gradually, over 2 weeks or less, and leave about 1 to 1.5 feet of water at the bottom. Before discharging, always test the pond to confirm compliance with NPDES permit requirements. This careful approach helps protect water resources and ensures regulatory compliance. Let's talk about the operating strategy for success. First, maintaining constant water levels is crucial. By keeping the pond levels steady, we ensure consistent loadings, which is essential for reliable operation. If you notice the levels dropping, check for open discharge valves, leaks in the levee, or plugged inlet lines. Conversely, if the water level is rising, you'll want to verify that all valves are properly closed and look for any infiltration sources that might be adding water unexpectedly. Next, equal distribution of flow and organic loadings across all ponds is vital. When one pond is receiving more or less than others, it could be a sign of internal clogging in the distribution lines, something that might not be obvious during a visual inspection. Ensuring each pond gets the same treatment helps maintain overall system balance and efficiency. Levee maintenance is another key point. Regular inspections help us catch issues early before they become serious problems. We should be on the lookout for leaks and signs of erosion. If erosion occurs along the water line, installing riprap can help protect the levee. Also, clearing weeds and mowing the levees regularly keeps them in good shape and prevents vegetation from causing damage or obstructing inspections. Finally, testing and observation are part of our daily routine. A quick visual check each day can tell us a lot, like a healthy, deep green algae color indicating good conditions. Additionally, testing parameters like dissolved oxygen, pH, and temperature once or twice a week at the same time of day helps us monitor the system's health and make adjustments as needed. All these strategies work together to ensure our pond system operates smoothly, efficiently, and reliably, supporting the overall success of our treatment process. When it comes to testing requirements and locations, consistency is key. Always collect samples from the same specific spot to ensure reliable data over time. For pond samples, I recommend taking samples from all four corners, about 8 feet away from the water's edge and just 1 foot below the surface. It's important to avoid stirring up the bottom sediment, as that can skew your results. Also, try not to sample during or immediately after storms, since weather can impact water quality and give you misleading readings. Now, let's talk about interpreting the water color. A deep green, sparkling color usually indicates that the pH is high and the dissolved oxygen levels are satisfactory. That's a good sign that the water quality is healthy. On the other hand, if you notice dull green or a lack of color, it suggests that the pH might be declining and dissolved oxygen could be lowered, which can stress aquatic life. Gray coloration is a sign that the system might be overloaded or that there's improper operation happening. Recognizing these color cues helps us quickly assess the water's condition and take appropriate action. This ties into the overall goal of maintaining healthy, balanced water systems. Now, let's discuss surface aerators for enhanced treatment applications. These aerators are particularly useful when you need to provide additional air during times like night or cold weather, or when dealing with overloaded ponds. They also serve as mechanical aeration systems for aerated lagoons, functioning similarly to activated sludge systems, but without the need for sludge return. It's important to note that these aerators typically operate on a timer, cycling on and off. We've conducted lab tests measuring dissolved oxygen levels to determine the appropriate cycle timing, but it's crucial to adjust these cycles based on influent variations and seasonal conditions to maintain optimal performance. A helpful rule of thumb for operation is, if you see foam on the pond's surface, it indicates that you should reduce the aerator's operating time. Conversely, if there's no foam, you can increase the operating time. A small amount of foam actually indicates the system is functioning satisfactorily. In terms of design, aerated lagoons tend to have a higher organic loading, ranging from 50 to 200 pounds of BOD5 per acre per day. They are typically 8 to 16 feet deep to allow proper sludge storage. Mechanical aeration not only helps to supplement or even replace algal photosynthesis, but also impacts the overall system's size and operational costs. While it may increase costs, it reduces the system's footprint, making it a practical solution for many treatment scenarios.